Module 4, Lesson 21, Writing and Evaluating Expressions, Multiplication and Addition. So far we've worked pretty much exclusively on just the inverse operations of addition, subtraction, multiplication, division. We're now going to look at expressions that are a little bit more complicated that are going to combine multiplication and addition together. And of course it's fun to think about how we are going to then use the inverse of those. All right, show and explain the relationship between the operations. This lesson is not so much about the relationship, although there's a little bit in there. We are going to represent real-life situations using mathematical expressions. And there is a little bit of experimentation that goes on here. We're going to say, what if this variable has this value? What happens? Okay, I can statements. I can represent real-life situations by writing expressions with variables and the operations of multiplication and addition. Use substitution to evaluate an expression for a given value of a variable, and write an expression to represent the relationship on a table of values. So we will continue to examine a table and try to determine, hey, what's going on here. And in class, this is a modeling exercise, so you will want some kind of manipulatives. Squares would work really well. We'll have just some pattern tiles that we'll use here in class. Something that you can manipulate and move and count. And what we have here is a pretty common situation. You go to the restaurant and you want to take a bunch of tables and put them together and see how many people you can seat. So the Italian Via restaurant has square tables that servers can push together to accommodate the customers. Only one chair fits along each side of the square table. And we're going to make a model of each situation to determine how many seats will fit around various rectangular tables. So we're going to go one step at a time here, and the purpose of building the models here is to think about what is really happening so that we can then express it algebraically. All right, so we're going to model a problem, moving the tables together. We're going to use square tiles to represent square tables. One person can sit along each edge of a table. We're not going to crowd. We're not going to do the two people in a seat. And the very first thing we're going to do is start small. All right, so we have a single table. Now, thinking about the rules that we've talked about here, we can put one person on each side of the table. So how many chairs could we fit around the table? Well, we could fit 4 of them. And the perimeter is 1 unit, 1 unit, 1 unit, and 1 unit added all together, and we have 4 yards, because it says the side of each table is 1 yard long. And we have recorded the information on the table. And now what we're going to do is say, all right, let's add a second one. So we've got one table here. Let's bring a second table and slide it together and combine them together and have 2 tables. So I've brought in my second table here. Now, what do you notice happens when that second table comes in? Well, I notice that the person who was sitting here no longer has a seat. So I can no longer fit 4 people around the first table. So I'm going to actually work with my model here and do some counting. So I've got the 3 people. And now here's my 4th person, here's a 5th person, and here's a 6th person. So if I have 2 tables, I can fit 6 people. And the perimeter is 6 yards, the distance around the outside of my rectangle. So what happens when I slide, oh, wait a minute, I need to ask this, sorry, thinking question. If there are twice as many square tables in the new rectangular table, why can't I fit twice as many chairs around it? If this were a ratio relationship, when I doubled the number of tables, I would double the number of seats. But that's not what happened. I doubled, but I only added 2 more seats. Why can't I do that? Well, I already kind of gave you a hint. There is no way for someone to sit here and someone to sit here. If we were going to have 8 people sitting around these 2 tables that are pushed together, they'd have to be really thin. And even then, they'd be in the middle of the table. They'd have to fit inside the little space there. it's not going to work. We're not going to squish anyone to sit in between there. So now what we have to start asking ourselves is, okay, what's actually happening mathematically here? How can I come up with an expression that is going to help me figure out how many people will fit around any number of tables? So we're back to looking at patterns. We're looking at the pattern that is happening as we add tables. So let's add another one. Now I've got 3 tables. Well, I used to have, well, let me draw my people who were here before. There used to be someone sitting on the end here, but that person has now been moved over to here. And I've got 2 people. So with 3 tables, I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 people and a perimeter of 8 yards. Now hopefully you noticed that we did not have a tripling here. We tripled the number of tables, but we have not tripled the number of people around the tables. Same problem. You'll notice there's no little people squeezed in between those spaces there. No paper thins. So what happens when we have 4 pushed together? Well, this person on the end is going to get bumped down again. And you'll notice that we've got 2 more seats there. So with 4 tables, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 people and a perimeter of 10. What about 5? Well, this person on the end gets bumped down again, and 2 more people get added on the sides. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, plus 1, 2. I've got 12. So pause for a moment here and ask yourself what is happening relationship-wise. What is happening to move me from here to here? What expression tells me what's happening there? And sometimes looking at 1 is not a great choice. Maybe it's better to come down here and look at a 3 or a 4. What is happening mathematically? What expression can I write to show this relationship? Well, as I look at this relationship, what I'm noticing here let me draw it this way. I started out with a single table here. I'll use blue so it doesn't wash out. I started out with a single table, 4 people around it. And I noticed that I've got these 2 people are sitting across from each other, and these 2 people are sitting across from each other. So I'm noticing that I have 2 pairs. When the second table comes in, I've still got the 2 people sitting on the ends. But I have added another pair on the sides. And when I add them up, I notice that I've got 4 here plus 2 here. So I have 4 plus 2. Up above, I had 2 plus 2. When I come to the set of 3 tables, I notice I've got 1, 2, 3, 4, 5, 6. So I've got 6, and then I've got the people on the ends. And then I noticed on the set of 4, 1, 2, 3, 4, 5, 6, 7, 8, I notice I've got 8, and I've got the 2 on the ends. I notice this 2 is a constant. I'm always adding 2. So I'm actually going to come over here, and I'm going to put a plus 2. The way that I have analyzed this, I know that I'm always adding the 2 people on the end. So then the question becomes, where am I getting these from? Well, I notice that 6 is the 3 times 2, the number of tables multiplied times 2. Oh, the number of tables multiplied by 2. So double the number of tables, because that takes care of these side seats, and then add the 2 people on the end, and I have the number of people sitting around the table. So kind of here, when we talk about another way to think about this, regardless of the number of tables, there is 1 chair on each end, and each table has 2 chairs opposite one another. There's always these 2 people on the end, and every table is going to fit 2 people. So drawing and looking at a model and then looking at some patterns can be a powerful way to analyze what is happening on a table that you're given. Now, it's probably not practical to make a model of pushing 50 tables together to make a long rectangle. And if we did have a rectangle that long, how many chairs would fit on the long sides of the table? And this gets back, this is looking at the pattern in a different way. So we noticed that for every table we have 2 people on the long sides. So if I had 50 tables, I'm going to have 50 on each side, and I've got a total of 100. And on the ends, I've got the 2 people. 2 chairs, 1 on each end. Notice this is yet another way of explaining how I came up with this expression here. So with 50 tables, I would have 102. And by the way, the perimeter would be 102. And if there are 100 chairs on the long side, and 1 at each end, how many total chairs? 102. Just did that. All right. And how many would fit around 200 square tables? Well, let's stop and think about this here. All of the 200 tables are going to fit 2 people. And then there are 2 people on the end for 402. Now, your brain might be struggling with you and saying, is there a way that I can think about this with 3 tables on the end? Sorry, 3 people at the tables on the end. And then I've got the tables in the middle. Well, I'm going to let you struggle and grapple with that if you would like. In my head, you probably want to do something with 6. And then you have to think about how you're going to add in the rest of the people. And remember, you need a situation that works with 1 table. And the reason I say 6 is because it's 3 plus 3. And I'm not going to say if it works or doesn't work. You go ahead and play with that if you want to. All right, we've already looked at this. All right, and I've already done this part here. I did it kind of out of order, but it seemed to fit right there. Double the number of tables, because there's two people at each table, and then add the 2 people sitting on the ends. All right, taking a look here at some pizzas. Oh, you know what? I'm going to come back to this for a second here. Let's see, 2t plus 2, 6, and 2t, 8. So we see that this is a multiply and add relationship. So if we're using inverse operations, how would we go from the number of seats to the number of tables? If we were to say, I need this many seats, how would we go the other directions like we did in the last 2 lessons? Well, we're going to need to use some inverse operations. So we're probably going to need a subtract 2, and we're probably going to need to do some division. And we're probably going to want to divide the table by 2. Of course, the other option you could try is 2 divided by the number of tables. I'll let you play with that a little bit. Now, the other thing that we're going to have to think about here is how are we going to follow the order of operations? We've done the inverse operations here. If we follow order of operations, are we going to, of course I am so silly, so very silly. And of course, now I'm going to have a brain lock here for a second. All right, so inverse operation, inverse operation. But I'm starting with the number of people. So I'm going to take the number of people, divide it by 2, and then I am going to subtract 2. Yep, because we're starting with the number of people. That's our what is changing in this column right here. Okay, sorry. It's morning. The brain isn't going to work exceptionally well. So let's do a little experimentation here. So let's take 8, number of people, substitute it in, divided by 2, minus 2. And 8 divided by 2 is 4, minus 2 gives us 2. But we knew that it was supposed to be 3 tables. So what went wrong there? Well, we have reversed the operations, but have we reversed the order of the operations? 8 divided by 2 minus 2. Which would give me 8 divided by 1, which would give me 8, which still doesn't work, so my brain is really not working on this. So this is one of those really awkward and embarrassing moments where I have to stop and think and look at my notes and say, okay, what had I planned to do with this part? It's always nice to see mathematicians get stuck because we know that they're like everyone else. Not that I claim to be a phenomenal mathematician here. All right, so I've got the people, and I want to go backwards. There we go. I'm going to take the people, and I'm going to subtract the 2. I'm going to undo the operation that I did last. And then I am going to divide by 2. See, the brain finally gets there. So I'm going backwards from the order of operations with this 2t plus 2. The first thing I did was the multiplication. The second thing I did was the addition. Well, I am going to do the inverse operations. So I'm going to subtract the 2. And then instead of multiplying by 2, I am going to divide by 2. And I am going to start with the number of people that I had, because I'm starting with the number of people, the number of seats. I'll use S. There we go. And I have to say I'm going to do the subtraction first. Yay! My brain finally woke up. So I know that that might have been really confusing, and if it was confusing, it'll come back later. But for those of you who like to make your brains hurt, thinking about how we can go this direction and then turn around and go this direction is powerful mathematics. All right, so we're going to take a look at the pizzas here. And we're going to try and figure out the cost for various numbers of pizzas, and we're going to determine the expression that describes the cost of having pizzas delivered. Because, of course, everything in life is about the pizzas. All right, so let's advance here. Pizza Queen has a special offer on lunch pizzas. It's $4 each, and they charge $2 to deliver no matter how many pizzas are ordered. And we need to figure out how much it's going to cost for various numbers of pizzas. Well, if I'm ordering one pizza, that's going to cost $4, and I'm going to have to pay the $2 delivery fee. So that's going to cost me $6. But I am going to do myself a favor here and say that I'm going to have the $4 for the pizza and add the $2 to give me a total of $6. I like to see what's happening as I work these problems. And eventually, we want to come up with an expression here to figure out how much any number of pizzas is going to cost. Well, if I order 2 pizzas, the pizzas are going to cost me $8, and the delivery fee is going to stay the same, at $2, and that's going to cost me $10. 3 pizzas will cost me $12, and the delivery fee remains the same, and I have a total of $14. Now at this point, a student could be fooled and say, oh, you just keep adding $4. No, that's not really what's happening here. We're looking at the relationship between the number of pizzas delivered and the cost. We're not looking at the relationship working vertically. 4 pizzas are going to cost me $16, and I will add $2, and I've got $18. And 10 pizzas will cost me $40, and the delivery fee stays $2 and will cost me $42. And then 50 pizzas, 50 times 4 gives me $200, must be a big party, and a $2 delivery charge, and $202. So now we need to stop and ask ourselves, okay, what do I actually have happening here? Now as I look down the chart, you'll notice that I was trying to think my way through what's actually happening here. I noticed that I add $2 every time. Every time I'm adding $2. So I'm going to add $2 on the end. That's constant. This $2 stays the same all the way through the column. What's changing is the amount I'm paying for the pizzas. And on this one, I notice I have just a regular multiplicative relationship. It's times 4. So I am taking the number of pizzas and multiplying it times 4. And then I'm adding $2. So if the principal wanted to buy a pizza for everyone in our class with our 24 students, I've got $4, and I'm going to substitute in 24 because every student gets their own pizza, but I have to remember there's a delivery fee. So I've got 24 times 4. I'm going to add 2 more, and I'm going to find out that it's going to cost $98 for the principal to buy a pizza for every member of our class. And of course, what I'm going to do is just charge a tax on each of you. So I'm going to get 24 pieces of pizza. So each of you has to give me a piece. So we don't need to worry about getting one for me. All right. Now, mathematical operations. Taking a look at what was actually happening within the table. We were adding the 2, and we were multiplying 4 by the number of pizzas. I know, a little out of order. Got to fix the slides. Now, if a booster, if a school supporter wants to come and spend $400 on pizza, how many pizzas could they buy? And I would challenge you to do that part that I messed up here and think about it as the inverse and go in the other direction. How are we going to go from this expression back this way? Well, going backwards, the first thing I need to do is take off the $2. And the next thing I need to do is take the amount of money and divide it by $4. So I'm going backwards. Inverse operations. The addition is now a subtraction. The multiplication is now a division. And I am taking the amount of money that I have, this $400, and I'm dividing it by 4. So $400 divided by 4 and subtract 2. 400 divided by 4 gives me 100 minus 2, which will give me 98 pizzas. And if I want to, I can check my thinking here by saying, okay, 98 pizzas, 98 times 4 plus 2. Well, 90 times 4 is 360, and 8 times 4 is 32. I have this feeling I've done something wrong. Why do I always manage to do this? Money divided by 4 minus 2. 400 divided by 4 is 100. Minus 2 is 98. 98 times 4. 98 times 4, 2, 3. 4 times 9 is 36. Plus 3 is 39. Plus 2 gives me 394. I still had $6. I missed something. $400 to spend on the pizza. Inverse operation. I want to subtract the 2. So I take off the delivery fee, divide by 4. Ah, of course. Because I want to subtract the first. Nope. I think I screwed that up. Because I'm not going to be able to get 200 pizzas here. It's not going to work. Works out to be 99 pizzas. And my brain is not going to come up with it right now. So I'll let you play with that. Because, of course, my brain is being really, really obnoxious. Which really bugs me. Of course it's going to bug me. Take off the 2, which gives me the 398. Oh, of course. I have the amount of money. I need to subtract the $2, and then I divide by 4. Ah. So $400, I'm going to take off the $2. So I end with 400, and the first thing I do is undo, take off the $2 that I added. That gives me the $398, and then I divide that by 4, and I find out there's 99 pizzas. Grr. All right. Thanks for bearing with me while I thought my way through that. I obviously need some more practice in being able to do that. But it's really powerful. It's really powerful. In the lesson materials, it says you could do some guess and check to find this. I think it's much more powerful if we start to think about how can I take these expressions this way. I start with the amount of money. I'm going to subtract the 2 and then divide by 4. Because I had 4 times the number of pizzas plus 2. Well, I'm starting with the money. I'm going to undo the add 2. And then I'm going to undo the multiply by 4. And of course, I have to have parentheses to say, hey, do the subtract 2 first and then divide by 4. So thanks for bearing with me while my brain worked that there. And if the pizza price is raised to $5 and the delivery price was raised to $3, create a table that shows the total cost of the pizza of 1, 2, 3, 4, and 5 pizzas, and include the expression. Well, I know that I'm going to be adding a constant 3, and I know that I'm going to take 5 and multiply it by the number of pizzas. So there is my expression. I'll let you do some of the maths there to figure it out. All right, I'll do one of them. 5 times the number of pizzas gets me 15 pizzas plus a $15 plus a $3 delivery fee gets me $18. 4 times number of pizzas, 4 times 5 gives me $20 for the pizzas plus a $3 delivery fee, which gives me $23. And of course, my brain's trying to work here. What if I had $50? How many pizzas could I get? Well, I've got $50 that I can spend. I'm going to take off the delivery fee, and then I am going to divide by the price of $5 per pizza. So I've got $47 that I am going to divide by $5 per pizza, and I'm going to find that I can get 5 whole pizzas, and I doubt they're going to let me buy 2/5 of a pizza, so I would say that I can get 9 whole pizzas, and I'm going to have a couple dollars left over. Alright, so some mathematical expressions use both multiplication and addition, and with your partner make up a new example of a problem that uses both multiplication and addition. So this is a chance for you to create a real life situation of your own. Alright, taking a look here, representing real life situations with multiplication and addition, and I kind of pushed the limits there, looking at some undoing there, so tacking on some subtraction and division. Undoing that multiplication and addition. So thanks for bearing with me while I kind of pushed it a little bit there. Substitution, we did plug in values and see what happened, and we did find the relationship on a table of values. Alright, relationship between operations, touched on it very minorly as I got stuck on some problems there. Alright, represent real life situations. Definitely worked on that, and we did some experimentation. So that concludes Module 4, Lesson 21. And if you've got any questions, make sure you talk to your teacher and make sure you do the problem set. I do appreciate you bearing with me in the video as I got stuck there, but it's important that when we get stuck, we don't just give up. We sit and we ask ourselves, what am I not understanding? What can I figure out?